So, hello and good afternoon, everyone. I'm just checking we are actually recording this time now, the live version. So, welcome all to today's webinar. The topic is selecting the optimal EDS system for your application. And my name is Martina. I work in communications here in Top Analytica, and I'm only here to help our today's speaker, Jyrki Juhanoja, and I will be moderating the Q&A. So as you can see, we have the Q&A tool available, and I encourage you to use it. So please leave comments and ask questions. We are recording this event, and we're trying to keep your participation as anonymous as possible. So feel free to share your questions, and you can trust I will not I will not tell anyone who's asking the questions. So please comment. We will share the link to the recording after the event, of course, and at the end of this webinar, I will also share a QR code that leads to a questionnaire where you can leave feedback from today's webinar, and I strongly would encourage you to leave feedback so we can make these webinars even better. But of course, today's webinar is going to be the absolute best of the best. So without further ado, it's my pleasure to give the floor to Jyrki Juhanoja.
Okay, thank you, Martina, and welcome all to this seminar about EDS systems. Okay, I take the laser pointer. So, okay. The topic is selecting the optimal EDS system for your application. And actually, you could have quite a big it is a huge topic which could include not only the hardware but also the software, automation, and special applications related to that automation procedures. Also, one topic would be integration with scanning electron microscope. You know that many vendors are offering these integrated systems. And finally, about the future of the EDS and how this artificial intelligence can be utilized in the EDS analysis, especially for the automation and special applications. But because we are short in time, I will focus only with hardware today. And I would say also that I'm not so much expert on the software, and with different companies, they have very different software and how to use them, and should have experience of all the systems. So the hardware is a little bit more common for all the companies, but let's see. First of all, there is a change on the EDS systems. The old traditional system was based on SILI detector on the left, where we have actually the first what the X-rays coming to the detector. We'll see the collimator, which is focusing the beam to the detector or preventing any stray radiation from the chamber. Then we have electron trap that protects this detector from electrons. Electrons are very harmful for this sensitive detector material. We have a window which is keeping this part of the detector in vacuum. We have actual the crystal, which is doing all the analysis work, and then we have an electrical components like preamplifier, and then we have a Goldfinger cooling this system. If we look at the new SDD silicon drift detector, it is quite different. Of course, we have a window in front of the detector. The SDD chip is situating here, and under that there is a Peltier cooling system which is keeping this detector cold. The temperature what we have here is probably something like -20 up to -50. Instead, what we had here we had liquid nitrogen cooling. So you see that the size of the detector part is much smaller than the previous one. And when we are thinking where we can utilize the EDS systems, we have a lot of applications, and those applications have different challenges. One could be, for example, the large area X-ray maps, other one beam sensitive samples, low KV analysis, trace element analysis, and so on. And then we have a lot of detector parameters which will affect how successful our measurement will be, like energy resolution, detector area, solid angle, window material, and so on. Lot of things. I hope I can go through most of this today. And finally, and maybe the most important, is also the price of the system. First, I will talk about the detector efficiency, and that is the number of counts what we are measuring per nano beam current in the electron beam, typically in the range of nanoamps. And this efficiency is not the same as the detector speed, which is in units of counts per second. And the measured intensity for a certain energy is depending on the amount of X-rays generated in the sample or emitted from the sample times solid angle times transmission of the X-rays before hitting the detector. And then from the electronics part, we have a dead time, which is usually given in percentage. So it is 1 minus this dead time, what is available for analysis. The detector or the solid angle is related to detector area. So if we have a bigger area detector, it typically have also a larger solid angle. And the detector sizes goes from maybe 10 square millimeter, what was a standard for silicon SILI detectors. Nowadays, the largest ones are around 200 square millimeter. However, the size of the or area of the detector is not directly giving the solid angle, because the setup is also important. The distance from the sample surface where the X-rays are generated to the detector surface. So this distance is very important. And this is a schematic figure how these are arranged inside electron microscope. We have the pole piece, typically this form. Some microscopes have different forms of the pole piece, so the solid angle is not only depending on the selected detector, it is also depending on the electron microscope. Typically the working distance between the sample and pole piece is around 10 millimeters. This distance is typically around 35 millimeters when we have these smaller detectors. Or in case of these large area detectors, it might be a little bit larger. So these values in sterradians are calculated by you assuming this sample detector distance, and then the relative solid angle is 1. If we have this distance 50 millimeters, then this solid angle is half from the previous one. And on the other hand, if you can shorten this distance, you can increase the solid angle markedly. For example, if this is only 10 millimeters, it is possible to get something like 10 sterradians in solid angle. Or this is a relative solid angle. And in specific detectors, this is utilized by forming this shape of the detector to have a special oval shape, so it can be placed close to this 10 millimeter distance, and then this 100 square millimeter detector can have a solid angle of 0.5 sterradians compared to this typical value what we have here. So this one is almost 10 times as effective as this detector here. Another way to avoid this problem of this tilted detector is to place a plate under between the sample and pole piece. It will be very close to the pole piece, and we can have quite flat detector. Typically they are called like flat cut, or so we have 4 different detectors, and then we have a hole in the middle, and electrons are first going through that hole, generate the electrons, X-rays, and X-rays are detected in these pieces of detectors. And that has been the standard configuration of this kind of detector, but nowadays there is also even higher solid angle available. What are the applications where the solid angle matter? First of all, it is typical when the amount of X-rays is small. One example is that the electron microscope, what we are using, for example, the high resolution SEM with cold field emission gun, it is not giving as much high electron beam currents as the ordinary tungsten filaments or the Schottky field emission guns, so it can be a limiting factor for this type of microscope. They are nowadays a little bit better. In previous time we were using, let's say, 20 kV voltage. The maximum beam current was only few nanoamps. And of course, if we decrease the voltage, then also the beam current drops. Other case is beam sensitive materials, biological materials, polymers can be very sensitive, and also some hard materials what you don't think will suffer from electron beam, like glass. Also some minerals. They don't see they don't show any change in the morphology, but in the composition will change. And maybe the most important is that when the analysis is done with low voltage, I mean less than 5 kilovolts, then typically the beam currents drops, but we have improved spatial resolution, and also this low voltage is good for light element analysis. In most cases, maybe 90% of the samples, this smaller solid angle can be compensated by increasing the beam current. Typical analyses are done with the E-beam currents of from 1 to 5 nanoamps. I was telling that glass can be a challenging sample or beam sensitive sample. This is an example where we have done a repeated measurement from a glass. Beam current was really low, dead time only 3%, 30 kV voltage, and 1 hour measurement time per spectrum, because I was interested on the trace element analysis on this glass. But also the analysis is from area relatively big. It was not a spot. If we are using a spot analysis, it is even more damaging for the sample. So this is a relatively gentle conditions for the analysis, but even though you can see that first sodium peak height was here, and when I was finishing the measurements, it was dropped to here. And if we look how the natrium concentration is changing in time, we can see that it was dropping from 2% to less than 1 during these measurements. And other reason to decrease the voltage is to improve the resolution. This is a geological sample, polished section, and we have different minerals. In the first map here, the voltage has been 15 kV, and you see that we can improve the resolution in the map by decreasing the voltage down to 10 kV or even down to 5 kV. And maybe the best lateral resolution is here, where we have on 3 kV, but by using very low beam voltage, we are not able to we are not able to ionize all elements. For example, in this case, potassium K lines are not ionized, so we cannot use the potassium K line anymore, and we could use the potassium L lines, but they are overlapped with carbon line, and this is of course carbon coated sample, So it was not possible to measure potassium. So maybe the best or optimal voltage for this sample is something like between 10 kV and 5 kV. This lateral resolution and analysis depth can be calculated or modeled by using Monte Carlo simulations. And for example, we can check this electron beam is coming here, and during this simulation process, the electrons are scattering here, and following the physical laws, they form some kind of pear-shape distribution where the electrons are penetrating. And you see that when we reduce the voltage, this volume where the electrons are able to generate X-rays is decreasing. Here the lateral resolution is around 500 nanometers, and if we go down to 1 kV, it is here something like 10, 20 nanometers. Here is more accurate calculation after these Monte Carlo simulations, and we have lateral resolution is now defined to be a spot diameter where 90% of X-ray intensity is detected, and analysis depth is also depth where 90% of the X-rays are coming. And we can see that decreasing the voltage will improve the lateral resolution and also the surface sensitivity. The EDS, or generality X-ray analysis, is relatively surface sensitive, so 1 nanometer layers or even monolayer thick layers can be easily detected with X-ray analytical methods in scanning electron microscope. But the drawback is that when we are dropping the voltage from 10 kV down to 2 kV, we are losing a lot of the intensity. So to have the same amount of the intensity, we now need 10 times more current in electron beam if we like to have the analysis done at 2 kV. Here is one example made with the flat card detector, which is very sensitive, have a very high solid angle. And here is the scanning secondary electron image. The working distance is relatively long. To have a better resolution in electron images, one would like to use smaller distances, especially at the low voltages. In this case, the voltage has been 3 kV. But we can see or obtain very nice maps showing very good resolution. So we have, first of all, this oxide layer, this part here. This is actually the surface of the original sample. The preparation was made with broad ion beam milling, so we don't need to embed the sample in epoxy. But we see that this oxide layer has different phases. The first or outermost layer is rich in manganese, and the inner layer it also includes manganese, but it is more enriched in chromium. We have some chromium also on this area, but the ratio is different. But what is special for this sample is that we have some silicon oxide particles between these metal oxide layers and the steel. And then we have some cavities here, and this silicon oxide and cavities may play an important role if we are thinking how well this oxide layer is bonded to the metal surface. Actually, from the image, I measured this resolution in the map to be something like 20 nanometers. There is another way to do EDS analysis with in scanning electron microscope with high resolution, and this is based on the fact that when we have a thin sample, let's say less than 100 nanometers, the incoming electrons are not so, during their path they have only few scattering effects, and they are not scattered as much in this short distance. So if we have a nanometer resolution here at the top where the electron beam is hitting the sample, we may have something like 5 nanometer, 10 nanometers on the depth of 100 nanometers. In this case, the analyses are better with a little bit higher voltages, 15 to 30 kV, because with lower voltages we will have more scattering in this thin section area. This kind of samples is typically prepared in focused ion beam SEM dual beam systems, where you can select the point where you like to make the analysis, because you are a little bit limited on the size of the sample, how big samples you can prepare. Here is a comparison where the analysis is done from the surface of the material. This is from Oxford Instruments. This is from the TEM lamella thin section used as a STEM-SEM mode in the scanning electron microscope, and same detector is used in both cases. Maybe this has a better lateral resolution. I think the main difficulty here is that this is very noisy image, so the collection efficiency hasn't been so good as it should be. This is what I have seen. This is image with the best lateral resolution for an EDS measurement in scanning electron microscope done on 25 nanometer thin lamella and showing a lateral resolution of 2 nanometers. This is from Bruker. And to have all the manufacturers included, I have also added an image from Geolla procedure from their web page, and in this case we have a nice map of semiconductor component, and you see that the measurement time has been only 5 minutes. So you can do these high resolution maps relatively fast. If we are talking about analysis with very low X-ray energies, I mean below 1 keV, then the one key factor is the detector window. The purpose of the detector window is, first of all, it is protecting this sensitive detector. So we have a window here, and then we have a vacuum between the detector and the window. So it must be vacuum tight and mechanically strong enough to withstand the vacuum on this side, and when you are changing the samples, then we have air pressure on this side. Typically for thin windows, we have a support grid made from silicon, and typical open area is maybe 70 to 80%. And that is giving this mechanical strength for this window. Then we have aluminum coating, and the purpose of aluminum is to stop the light hitting on the detector surface, because the light, when it is hitting the detector, it is also giving noise and to the spectrum in this energy range, so it will destroy the nice spectral resolution on this area. The thickness of 13 nanometers is not 100%, and doesn't have a stopping power of 100%, but it is, most of the light is absorbed by this thin aluminum coating. On the detector surface itself, we have also so-called silicon dead layer, and that is coming from the manufacturing process. So it is a silicon layer which is not giving any X-ray counts. So it is, and therefore it is called dead layer. And it actually also affects on the transmission of the X-rays. Typically, the manufacturers are telling that the thickness of the dead layer is 13 nanometers, but my experience is that it might be larger, and it might also be that if the detector is getting older, this dead layer thickness is increasing. So this polymer, there is actually probably two commercial polymer or window materials. One is so-called MOXTEC AP 3.3 or 3.5. It is typically some kind of Kapton polyimide film, and the other polymer which is used is the Mylar film. Mylar is not as good as this Kapton. And then there is an inorganic films like silicon nitride, and because this is stronger than the polymer materials, it can be thinner, and actually if we calculate the transmission, which is a function of the film thickness and film materials, we can see that the silicon nitride film or foil is having a better transmittance than the AP3.3. And especially this is related also what elements you are looking for. If we have a polymer material which has a strong high amount of carbon, then it is very strongly absorbing nitrogen. We can see that the difference between the mylar and the silicon nitride is almost tenfold. For the thickest mylar, maybe 3-4 times high, better for this thinner mylar foil. But anyway, the material is very, very important when you are looking the transmission in this range. In windowless detector, this calculation is only for this silicon dead layer. And if we are looking for example, calcium, if our sample include calcium and we are interested to have it analyzed with the low voltages using calcium L-line, we can see that windowless detector gives almost 10 times more current or signal than these polymer windows and about 2 times more than the silicon nitride. And the difference is even bigger if we go to the lowest element, boron, beryllium, lithium. Lithium is only possible to measure with the windowless detector. Beryllium and also beryllium boron, maybe the windowless. They are telling that you can see this with these windows, but then the beryllium amount must be very high in the sample, and same is true for lithium if we are using the windowless detector. Okay, this is my personal opinion, so you can skip it if you like, but I would say that for low energy work, especially if you are interested to X-rays below 1 kV, this is the best option. It has no absorption in window, high solid angle, but the problems are sensitivity for the light and the electron trap. It's very difficult to build an electron trap here where the sensor is very close to sample. Distance is only maybe 10-15 millimeters. And also this protection during sample exchange, because we don't have any protection for the crystal here. There is some tubes and we have some shutter mechanisms on those tubes which will save these detectors when the microscope is in air. And these types of detectors are also very expensive ones, maybe the most expensive of detectors. Then we have this Bruker flat cut type of detectors. The SDD detectors are located here. Here is the hole where the electrons are coming through the detectors. Here is the thin solid Mylar film, and then we have more film options if we like to have more voltage on the microscope. So we can select the filters what we use based on the X-ray electron voltage of the scanning electron microscope. In our case, we have a thinnest Muller window, and with that window, we are able to measure or use the voltage of 3 kilovolt on the microscope. If we put the medium thick filter, we can go up to 8, and when we have the thickest Muller, we can go up to 20 kV, but that is absorbing everything below 1 kilo electron volt in X-rays. Because this has also 4 different CDD chips, it is also very fast in spectrum collection, coming to that point later. And also when we have different several detectors in different orientations, we can compensate the shadowing effects with rough samples. In our case, this filter what we have is not a vacuum tight filter, so we have to warm up before taking the sample out from the SEM, and then we have to because if it is cold when we let air in the chamber, all the water vapor in air will be condensated on this cold surface on the detector surface. Because we have a Mylar films which is stopping the electrons going to the detectors, these electrons are actually generating X-rays in the filter, so we get an additional carbon and oxygen X-rays from the filter. And also this type of the detector is a very pricey one. If we are talking about this so-called normal detectors, I would say that the order is following the size of the solid angle. And these kind of detectors are very good choices in the basic EDS work. As said before, the silicon nitride window has better transmittance than the MOXTEC, but on the other hand, it is not available for with big detector areas. One thing what you could consider is to have 2 60 square meter detectors instead 170 square millimeter detectors, because you have also almost the same price, almost the same solid angle, and then you have 2 detectors which is giving faster mapping for the samples and less shadowing problems when these detectors are located on different side of the chamber inside microscope. Here is some typical prices for different detector sizes, and you see that this 170 square millimeter detector is very expensive one. Then we come to detector speed, and this output count rate depends on the electron beam current, sample material, and detector efficiency, and the processing speed of each X-ray quanta. And if we are thinking about what is the maximum output from the detector, then this is depending mainly on the electronics and selected processing time. And this high detector speed is needed for X-ray maps. If you are satisfied with low quality map, then you need something like 1000 pixels counts per pixel. But if you need quantitative map, or you like to map minor elements, then you need 10 times more counts per pixel. This is some mineral samples. The blue spectrum here, it is with 1000 counts, and the red one is 10,000 counts. That is the total amount of counts in the whole spectrum. And if you have only 1000 counts, you cannot say that you have iron in the sample or sodium, which is located here. So the time what you need for different map sizes, it is depending on the image size, how many counts per pixel you need. For example, here we have this very low resolution map or image and low quality map. But even for that, you need something like 65 million counts. And that if you have a detector which is giving, or the count rate, maximum count rate is 100,000 counts per second, it will take 10 minutes. If you have a fast detector capable for 1 million counts per second, then the time is 1 minute approximately. 10 minutes versus 1 minute, that difference is not so big. You can live with that. But if you increase the image size or the amount of the counts per pixels, you will end up with very long measurement times. And in this case, 2 days against 6 hours, that is a big advantage to have a fast detector. So especially, and this is not a very big area or amount of pixels what you have in the sample. You can think about a thin section, geological thin sections, which is 50 millimeters times 30 millimeters, and you like to make the measurement with 10 micrometer resolution. You have a lot more pixels in that sample, and this is probably 1 week or even more. And if you can do the same thing in 1 day, it would be an advantage. Other application where the trace element analysis is, or the high speed of the analysis is important, is the trace element analysis. This is a typical sample from the glass where we have certain trace elements concentrations given here, and you can see maybe you see from this image that you have iron, maybe zinc, copper, but some of these elements are not so small peaks that you don't see it directly from the spectrum. What you need to do is to subtract the background, and then you get the spectrum like this. And now you see what you have in your samples. This with normal EDS, it took 4 hours. With FlatCAD, a little bit more than 1 hour, and you can get very, or let's say, same level of detection limit than in microXRF, where you have a shorter measurement time of 30 minutes. There is some problems you can see here in the Chromium. You have this counts here. They are not coming from the Chromium. It is a pulse pile up, some peak of silicon with calcium or something like that. And same is true also for manganese and so on. So you have to be very careful on the when you are subtracting the background from the spectrum. So the processing time and the dead time. Processing time is actually the time what is needed to get the energy calculated from the incoming X-ray quantum. And if you have a longer time, you can get a more accurate value for the energy, and that gives better energy resolution. So for example, if you are using this 4 microsecond processing time, you get this typical value of 125, what is typical for modern EDS systems. If you decrease the processing time to 1 microsecond, you may reach the resolution of 130, and 0.2 microseconds, you get the resolution of 140. The advantage of have this fast counting is, of course, that if we have 1 million counts per second coming to sample, you can get out almost 1 million counts from the system. So it makes the analysis much faster. The manufacturers are not naming this processing time as with fixed values. They have some relative values like 1, 2, 3, and so on, or the broker, which is giving the maximum output for certain processing times. And these values, what are giving, they may vary by the detector type. As I said, when the detector is processing a single quantum, the detector cannot accept other X-rays, and we are losing analysis time, and that lost is called dead time. There is in the system, there is a very fast circuit which is only detecting the income of the X-rays, and if there is 2 X-rays coming in a time window too short, it is not accepting those counts, and it is reacting this, because if the system is accepting these 2 counts, the actual energy what the detector calculates is the sum of these 2 counts, and we will get some peak in the wrong position in the spectrum. So this pulse pile up circuit is removing some of these pulses coming very close to each other, but not all. And therefore the manufacturers are using also corrections in the software which are removing these sun peaks. However, these sun peaks can be problematic in quantitative analysis, and the user should select an settings where the dead time is less than 20%. If you like to have a very fast mapping, then you can increase the count rate to close to 50% dead time. And then some mentions about the lifetime of these detectors, because always when these X-rays are coming or hitting the detector, they are a little bit damaging the detector, and that damage will cause that the resolution of the detector will decrease. And here is a typical plot where you see that after a dose of 1 to 12 X-rays per 10 square millimeter, you start to reduce the resolution of the detector, and when this dose has been 10 times larger, this change in the resolution is very rapid, and you should replace the detector in this point. What this 1 to 13 corresponds in real life, if you think that you are using a continuous X-ray source and measuring it continuously, it will be 116 days if the detector input is 1 million counts per second. This is for 10 square millimeter detector. If you have a larger area detector, it will be, of course, proportional to the area in 30 square millimeter detector. It is 1 year. About the energy resolution, I think the manufacturers are very keen to show what is the best resolution for different detectors and comparing to other competitors, but that is, in my opinion, that is not so critical. Because if you like to use this fast count rate, then this resolution is close to 150. However, with this fast counting, these differences between detectors can be large. But typically the manufacturers are not specifying these values. You should note that detectors with smaller areas have a better resolution than the detectors with large areas. If we think about the quantitative point of view, maybe the more important thing is what is the shape of the peaks, because we do very often peaks are overlapping and we have to make this deconvolution of the peaks, and then the shape of the peaks is very important. However, the application where the resolution is critical is the low energy analysis, because in that spectrum area the peaks are very close to each other, and typically the manufacturers are specifying the carbon peak resolution, and that is much more important than the resolution at manganese K alpha. So the conclusions. If you like to have energy analysis on low energies, then you should have a large solid angle and high transmission window. If you like to have a fast mapping, then you need the fastest electronics, and maybe you would like to have more than just one detector. Now it is a limitation also from the SEM, how many detectors you can add on the microscope. Also for rough samples, setup with several detectors will reduce the shadowing effects. Okay, this was all what I had prepared, and thank you for listening.
Thank you so much, Jyrki. I know we're a little bit over time and you're getting much deserved applause. It's still time to have a couple of questions if you have any. I don't see currently anything in the questions and answers tool. You can use the chat as well. Jyrki did mention earlier that he would have such a thorough presentation prepared for you guys that there wouldn't be any questions, but you're welcome to prove him wrong if you do have any.
Yeah,
and also
yes.
we're open to comments.
Yes, and also if you have something you like to discuss, you can always send an email also for me.
Absolutely. We are very happy if you reach out to us in further questions. So if there aren't any, I'm going to go ahead and find the chat and paste the link to the feedback form if you have a minute to fill it up. I will also share my screen to give you the QR code that will also lead you directly to the same survey. So we thank you all for joining, and we will be happy to welcome you to our next webinar as well. The title is a little bit uncertain so far, but the webinar is going to be on April, so hope to see you next month. And stay tuned. It will be published on our website as soon as we get the title tweaked. So thank you all and see you next time. I will now conclude the webinar. Hope to see you guys again. And thank you, Jyrki, once again.